Okay. Let's continue on. Okay, so what have we done so far? We have said, hey, here's a recipe for a different recipe for constructing a random field. We saw the convolutional recipe last week where you'd start with white noise and you'd move a kernel over that surface. Here we are constructing a random process through sinusoids. And what we get is an expression for the covariance of that random process. So the next idea is to go from a finite number of frequencies to an infinite number of frequencies. And now our function y, rather than being indexed with j's, it's going to become a function of frequency. And what Fuentes and Rich say is take L2 limits of the expression 1 on the previous page, and what you obtain is this. You get an integral instead of a sum, and this y becomes dy of omega. Fuentes and Rich don't provide details. I'm going to provide just a smidgen, a small amount of details here soon, but let's take Fuentes and Rich at their word and say that if we take limits in the right sense, we can get this expression here, where now we're integrating over all possible frequencies. We're taking this uncountable collection of frequencies, but given any omega in that uncountable collection, we can think about the cosine and sine wave that comes out of this expression here. And what we've got is a random element, which is which would be given by the, drawn from this density y. Okay, so the Rich and Fuentes say by taking the L2 limits of 1, we obtain the spectral representation of all mean square continuous weakly stationary processes. So this statement is not obvious, and what's really not obvious is this all here. It says we started with what feels like a pretty determined. We started with a recipe, right? We said we can build these processes from these sine and cosine waves, and this. But here it says that this is a spectral representation for all stationary processes. So you give me a stationary process that wasn't constructed in the way that we just were thinking about, we still get this spectral representation. And this is exactly the spectral representation theorem. So let me jump down here to the spectral representation theorem. The spectral representation theorem says, I guess really what I state the spectral representation here. It says that any mean square continuous random process Z can be written this way. And so it's not saying that for any function here, there's a Z, but what it's saying is for any Z that is mean square continuous, there is a random process Y such that Z can be represented this way. Y is called the spectral process associated with stationary process Z. And pause for just a second. Have all the random fields we've discussed been mean square continuous? When we think mean square continuous, that should put a thought in our mind of something about the covariance function. What we know is that the covariance function has to be continuous at 0, right? When for lag 0. And we have thought about processes which had a jump there. We talked about the nugget effect. And so the what this is saying is we're excluding those sorts of processes. We're not considering processes which have that measurement error built in. And so if we have a mean square continuous process, then we can get spectral representation. And so kind of big picture, if you're thinking theoretically, some people are very uncomfortable with the notion of a process that isn't mean square continuous. And part of that uncomfortableness is that the spectral representation doesn't exist. You can't have this spectral representation theorem. A way to reconcile that could be to separate the sources of variability in the way that we talked about earlier, where we said our general process E breaks down into different components, W and eta and epsilon, where W was smooth, eta was this microscale process, epsilon was this nugget effect, or this measurement error, and then the W would be mean square continuous. So anyway, just putting this statement into the big context of what we've learned, spectral representation does require our process to be mean square continuous. Big notion is, give me a stationary mean square continuous field. There is a Y here that corresponds to it. Okay. We can't really picture the Y because it's random, but we can talk about its properties, and particularly we can talk about the expected value of dy squared. If you want to think of this as a variance, you should be sort of thinking of it as a variance, because back here we were thinking of this, that their notation f here in the finite case was on purpose, where we were thinking of this is something that describes the magnitudes of which this random variable can take on. Well, this f, this capital F here, in the well, I guess I'm getting a little bit ahead of myself. Let's look at the next slide here. Or is it? Oh, okay. I have gotten ahead of myself. Sorry. We'll talk about this F is going to appear again here in just a second, but we will define F to be the expected value of this dy squared. I've got the absolute values because this y is complex. We're coming down to a single number, and f, of course, is going to take on positive values. So this is sort of the analog of the right-hand side of figure 5.1. We can talk about the randomness in the y's by sort of their magnitudes here, and by messing with these values f, we're going to induce different properties in our random fields. Or thinking about it the other way, if we start with our random fields, that's going to tell us something about these f's, which describe the magnitude of the randomness in y. Okay. Fuentes and Rich kind of gloss over the L2 limit piece, but what's sort of going on behind the scenes is we had this expression for z as a sum of m of these guys, and what we're going to do is we can think of a sequence of processes z indexed by m, the number of waves that we're going to use to put together, and then we take the limit of this as m goes off to infinity. And the L square limit says that if there is a z which this thing corresponds to, then that z is given by this expression here. So I'm not going to get any more deeply into that, but the L2 limit, of course, is this mean square limit that we talked about before. Okay, so our takeaway message at this point is that we can imagine random processes being created from sinusoids with random coefficients, but really the spectral representation theorem gives us the reverse of that. It says that, and we didn't prove the spectral representation theorem. I forgot to mention this, but Fuentes and Rich say, the proof is tough. The spectral representation theorem may be proved by various methods. You can use Hilbert space theory, you can use trigonometric integrals. Doing so we would spend too much time on these spectral methods. I want to give you an idea of spectral representation of random fields, but please know that there's a lot more that could be done. We could spend a whole month doing spectral representation. So spectral representation theorem, which we didn't prove, says that any mean square continuous random field can be written in terms of sinusoids and a spectral process y, which exists in the frequency domain. So in some sense, what it says is the randomness in the spatial domain can be transformed to a function which describes randomness in the frequency domain. Which brings us to Wagner's theorem. Wagner's theorem makes the link between our spectral representation and our covariance function. So it says so imagine we have a covariance function. Again, think of S here as lag, not location, our covariance function. We've written in certain ways, but given a random process, it can be written in terms of our spectral representation. So F we defined earlier, it's the expected value of the absolute value of y squared. So this is just giving us some magnitude, and our covariance function is going to come out of this. So we've jumped from y to f. We defined f before, and another thing that's going on here is this f doesn't really need to be absolutely continuous in some way. You can think of if you want to think of this as a random thing, don't think of it as a density, think of it as a distribution. And we'd have to define the Radon-Nikodym derivative of this thing to sort of talk about it. But this is measure with respect to this distribution. If f has density with respect to Lebesgue measure, then we'll call it a spectral density. We can then denote that by f, and we can get the inverse transform. So notice that this is a transform essentially where our covariance functions on the left-hand side and the spectral density is inside the integral. Here we've reversed that role, so here's the inverse transform where our covariance function is inside the integral and our spectral density comes out. So what this says is if I start with a covariance function and I want to get the spectral density, assuming our covariance function is nice enough such that this thing is that our spectral density comes out being smooth, here's our recipe for doing it. We're not going to prove Wagner's theorem, but we can our takeaway message is basically there's a one-to-one relationship between the randomness of the frequency domain and the covariance process in the spatial domain. So this is where we wanted to be. This is our transformation. I said at the outset of this randomness thing, we need to transform a function which describes the randomness in our process. That's the covariance function. We had to do a little bit of work of that, but our transformation is given right here in Wagner's theorem. One other thing that Wagner's theorem gives us is a way of showing that a function is positive definite. So we said that to be valid, a covariance function has to be positive definite. And that's a hard thing to prove. But what do I know about a spectral density? It's like a probability density. It's got to be positive. And so if I come back here, if I start with covariance function, and I can show that this results in a spectral density that's positive, then I've done. Then I've shown that this is a valid covariance function. I've shown that it's positive definite. So let me just read this to make sure I've covered everything that I wanted to say. Bachman's theorem states that a continuous function C is non-negative definite if and only if it can be represented in the form where f is a positive finite measure, or if we can jump to densities where little f is greater than or equal to 0 for all omega. So this is a way of checking to see if a given covariance function is valid. We can jump to spectral density land and do that much more easily than we can do it in standard representation land. And if I want to create a valid covariance function, I can start with any valid spectral density and integrate it to get a valid covariance function. Would that be useful? Well, you'd have to know what the useful spectral density would look like. So that can be challenging from a practical point of view. Finally, we talked before about how the power spectrum, basically we decomposed the total power of the function into the power spectrum. That was back in the Fourier series. We first saw that. And there is a connection to total power here. Before we had deterministic amplitudes to our sinusoids, now they're random. We're going to think of the expected value of z squared as being our power. Does that sound about right? Well, if you look back at our definition for power, we said it was the integral of the function squared. We had those wiggly functions, the not so wiggly function. We said a way of putting the number on the power, the activity going on with this function was to square the function and integrate it. Well, hey, guess what? That's exactly what happens with an expectation, right? We're squaring it and integrating with respect to the density. We also know that this expression gives us the covariance at lag 0, right? This is an expression for variance, assuming that z is mean 0. And so the covariance function at lag 0, well, this just says what I said before, that this is variance, right? And so if c of here s is lag is given by this expression. If I plug 0 in, I plug 0 in here, that's e to the 0 is 1. And so we have the integral of f. And so what we said before was the power was equal to the sum of those cn squares, right? Well, f is written already in terms of squares, and rather than a sum, we've got an integral. So all this is saying is that notion of power, that notion of taking all of the magnitudes of those coefficients, which here are random, taking all of the magnitudes of those random coefficients and adding them up or integrating over all possible values gives you the total something. What's the total something in this case? It's the total variance. All right, so that is all I'm going to talk about for spectral representation of fields. It will come up occasionally throughout the rest of the course. It's certainly going to come up in the next couple of homeworks and probably in some form on your midterm. I want you to know something about this, but I also recognize that it's hard. Transforms are hard because they're hard to picture. And I want you to have some general ideas of what spectral representation means. We certainly have not gone into things as deeply as we could. Neither Schabenberger and Gotway nor the Fuentes and Rich source that I'm pulling from go in as deeply as one could. And doing so would require a whole lot of time. But hopefully at this point, you got some notion of this spectral representation. And where does it fit into the big picture? It's yet another way of thinking about these random fields. So we have a number of ways of thinking about these random fields. We've talked about the model representation, we've talked about the convolution representation, and now we have this spectral representation. And it can be useful, particularly if you're going to work in this area, to be able to bounce between these various representations. All right, that is it. I think this is all I'm going to record for the week of September 11th, September 13th. I will see you when I am back from DC on the following Monday.